Okay, let's start our third lecture. And as usual, let's just quickly review what we did last time on Tuesday. So we were discussing, first on Monday, we did the kinematics. And then on Tuesday, we started the dynamics. And we were discussing scalar particles. And that's why we were only concerned with kinematic invariants for massless particles. Okay? So we introduce a matrix for m particles that contains information of the kinematic invariants. And this matrix had a nice property. Well, in fact, the property that I'm about to ask you about, or that I'm supposed to ask you about, it's the property that makes this into a physical object. So this is a symmetric matrix with zeros in the diagonal. So what else do we have to impose so that this becomes a matrix that parameterizes the scattering of m particles, of physical m particles? So there is a property we have to impose on the matrix. Do you remember what that property was? It had to do with a null vector. So what's a null vector we have to require that this matrix has? You remember? Well, it should be in your notes. That's a good thing about having notes, right? So what we have to impose is that this matrix, oh, that's the problem. Last time I was using this k and not this k, right? That's why it didn't quite work. So this is physical if the vector 1, 1, 1, 1 is a null vector. And then we also said, well, if you have something like that, something where the sum of the rows and the sum of the columns add up to 0, then we can define the determinant of the matrix because it always gives you 0. No, but then what we said was that there was a nice way that mathematicians have of defining the determinant of this matrix so that you get something more interesting than 0. And they put a prime in there. And the way they do it is by removing any row and any column of this. And since the answer is independent of the row or the column that you choose to delete, so that you produce a submatrix that has non-zero determinant, then this is a canonical definition for whatever information this thing is carrying. Okay? All right. Then we went on to define another matrix. So let me actually not make the same mistake again. Now you all remember what this matrix is. This matrix was similar to that one. What we did was to divide by the differences of the locations of the punctures or the mark points on the CP1 that we were dealing with. So exactly the same matrix as before, but now dress every kinematic invariant dressed by its corresponding collection of mark points. Now, this matrix also had some special properties, or we actually imposed the special properties so that it will have a physical meaning. So what's the special property? Well, we impose the same thing as the first one, right? We said that this vector, we impose that this vector is a null vector of this matrix. And that condition implies that the sum of the, say, the sum of all the columns is equal to 0. And that means that SAB over sigma A minus sigma B, if we sum over B from 1 to n, is equal to 0. Okay, always remembering that we're not supposed to include the B equals to A term because we get a singularity if we do it first. But if we just sum over these things, this is a better way of imposing those conditions or explaining that. Now we said that if n is an even matrix, if n is even, and we get an even matrix, this matrix is antisymmetric, so it must have a second null eigenvector. And what was that? Now that one is trickier because it's not in the first part. So it was something constructed out of the mark points, the locations of the mark points, sigma 2, sigma 3, all the way to sigma n, also happens to be a null vector. And that's why for n even, if we want to define something that makes sense, something like the determinant of this object, but given that A is antisymmetric, what we really want to define, now you're all professional with antisymmetric matrices, and you will never, ever again compute the determinant of that thing. You will always compute what? The Pfaffian. Yeah, exactly. You can impress your friends by telling them, yeah, of course, let's compute the Pfaffian of the matrix. But in this case, sadly, we also get 0. But we found a way of generalizing this idea of putting a prime and defining something that doesn't depend on the way we define this. So we decided to call this Pfaffian prime of A, something that we construct by deleting 2 rows and deleting 2 columns, well, the other way around, 2 columns or 2 rows. So let's say that we construct the submatrix where we delete the 2 columns I and j and the 2 rows I and j. Then the submatrix that we get is still antisymmetric. Therefore, we can compute the Pfaffian. But in order to get something that is independent of the choice, and that was your homework exercise, which I'm sure you all did, is we have to divide by the difference of the sigmas. Okay? Now, you see, I hope you can see a pattern here. We start with this matrix. We turn into this matrix now. Now it sounds like we could define even a third matrix. And we have to come out with a name. So let me propose phi n. So if somebody put a gun on your head and says, define a third matrix, what would you do? That follows the pattern. What would be the next thing to try? Yeah, but what are the elements? So you would try something like this. You would try, well, 0, it sounds reasonable. And then you would try S12. So maybe this guy here was really sigma 1 minus sigma 2 to the power 0. This one is sigma 1 minus sigma 2 to the first power. Then the next one you would say, why not make it square? Okay. Okay. Now this matrix is symmetric, right? Because we went from symmetric to antisymmetric, now it's symmetric. Now, what do you think this guy has as a property? So tell me, is there any null eigenvector? What do you think?
Probably also 1, 1, 1.
Okay, probably also 1, 1, 1, 1. It turns out, no, it doesn't have any null. So isn't that annoying? So the next one you try it, then it doesn't have it. But of course, we wouldn't stop there. Said, no, come on, there must be something interesting. So why don't we force it to have the vector that we want? So we want this guy to have this null eigenvector. How does it fail to have that thing? So when we multiply this with this vector, we get the sum of these guys, right? So if we were only allowed to trick these guys into having this null eigenvector, so if we are allowed to switch these zeros into something so that we could have this null eigenvector, maybe we will be in business, okay? So can everybody see that? So right now, if I multiply this matrix with this, what do I get? The sum of these guys. I don't get 0 as the first component here. But let me actually write it. So the first component would be the sum of SAB over sigma A minus sigma B squared from B equals to 2 to n, right? So that would be the first one, sorry, and S1 here. So I don't get 0. But what if I put this quantity with a minus sign in this entry? Sounds like cheating. Well, but once again, I'm giving the talk, so I can cheat. So let me do it. Let me define here phi 1, 1, phi 2, 2, and all the way. So you see, it was perfectly designed to just become phi n n, where phi AA is our cheat factor. So we're cheating by putting minus the sum of the things that we want to cancel. So you're allowed to cheat as long as you get something nice out of it. So we did this, and we got this null eigenvector. But that's not enough. If the cheating allows you to get something else, then it sounds like it was a good idea. So how about this vector? You didn't say there was no equal sign here. Well, now that you have this, if you are on the support of these equations, it turns out that for this new matrix, or our improved matrix, this is also null eigenvector. So it sounds like it was great. But now if we follow the pattern, it seems that we're missing something. Right? So this guy had one null eigenvector. This one had 1. This one has 2. So it wouldn't be nice if this one had 3. Well, actually, it does. You can also have as a homework exercise to show that this is also null eigenvector. All right? And then what are we supposed to do? What would be the next step? To define, just follow the derivation. So we define the determinant prime of that matrix, the Pfaffian prime of this matrix. So let's define the determinant prime of this matrix. How many rows and how many columns are we supposed to delete? 3. So let's delete. This is going to be the determinant of the submatrix. When you delete ij and k, the ij and k rows or columns, and p, q, and r for the other ones. And what do you have to put in order to make this independent of the choices that you make? Well, you see the pattern. Here, what we did was to construct the 2 by n matrix made out of the null eigenvectors. And then the things that we removed, we just took those 2 rows and computed the determinant, and that's the thing that we put in the denominator. So here we can do the same thing. We can take the same 3 vectors and then collect the ith, the jth, and the kth rows and make a 3 by 3 matrix and compute the determinant of that object, which I'm going to denote as ijk. You can convince yourself that the determinant of that submatrix of this matrix of null eigenvectors of the matrix phi happens to be the difference of sigma I, sigma j minus sigma k, and sigma k minus sigma I. And then part of your exercise is to show that if you divide by this object for ijk here and pqr here, then you get something that is independent of the choice that you make and is a canonical object associated with such a matrix. Well, that part, I don't know how you're going to prove that it's canonically associated with that, but in any case. It's independent of the choice, so it seems like a nice thing to try. OK, so this is the perfect point to give you an exercise while I erase the other blackboard, which is what happens if you go to the next step. OK, so try to work it out. What would you do for the next matrix? You will put a cube here, right? OK, so you have exactly 3 minutes. Well, maybe more. OK. Let's try this, this, and this. What happened? OK, almost done. So are you done? So of course, after teaching you how to cheat, I'm sure you cheated again, right? So you found one null eigenvector for such a matrix. Now the question is the matrix you found something nice? Something that does something unexpected on the support of the scattering equations? Well, the answer is sadly no. Now the question is why? Why does our luck runs out with the matrix that I wrote? Why only 3 matrices? Is there any other thing that is only 3 in this lecture? Well, this is the 3rd lecture, but that's not. It's a. Oh. OK. Anything else that has dimension 3 that we have discussed? That's the only space-time that we haven't discussed, the 3-dimensional one. So don't remind people that. Yes. Well, remember, we're working with a Riemann sphere. And we said that the Riemann sphere with mark points, its complex structure can be defined very nicely by giving the location of the mark points modulo SL2C. And SL2C has dimension 3. So in fact, what we're seeing there is just a consequence of SL2C working out its magic on these objects. So we just ran out of group generators, and that's why we stop at 3. Okay? Now, next, we said that the scattering equations which were defined to be, we start with this object, and we impose that the EAs are 0 for all A's, would allow us to connect, they connect our space of kinematic invariance with a modular space of genus 0, Riemann surfaces with M mark points in such a way that every time you have a kinematic singularity that you would like to have, the equations take you to that place in the moduli space. And moreover, they produce for you the factorization that unitarity is requiring. Okay? So not only locality, but also unitarity would be guaranteed if we are able to construct objects that are nicely integrated over this space. So the proposal was that we can start with the scattering amplitude for any theory written as an integral over this moduli space on the support of these scattering equations times some integrand that we are supposed to determine, which contains information of the particles, such as wave function, momenta, and the location of the mark points. And these things were supposed to only appear as polynomials, because all the pole structure is supposed to be guaranteed by the integration over the moduli space. So this formula, as it stands, is actually ill-defined. So it doesn't even exist. The reason is that we're supposed to mode out. Think about this as a little gauge theory that we have there. And the gauge group is SL to C. So we really have to mode out by SL to C. And there is even a bigger problem that you see here. These equations, remember, for 4 particles, we were able to get a single equation that controls all of the other ones. So out of the 4 equations that we could write, only 1 was independent. So if we put here all 4 equations, we would be in trouble. But let's pretend for a moment that we can put all 4 equations. So once you have delta functions, what do? To compute anything with delta functions, what you're supposed to do is to change variables. So you introduce new variables, which are the arguments of the delta function, and all you do is to make the change of variables and pay the price of the Jacobian. So what is the Jacobian of this change of variables? So once again, we are pretending. After all, nobody's looking, right? So what we're doing. So let's pretend that all these equations are independent. So if that was the case, let's pretend that EAs are independent. And therefore, when we compute this, what we do is to say we introduce new variables UA, and we compute the Jacobian. Okay? So let's now compute the Jacobian of this thing. So the Jacobian of this change of variables would be the following matrix. We take is the matrix constructed by taking EA and taking derivatives with respect to sigma B. Okay, so I'm going to do the easy one, right? I'm going to take the derivative with respect to sigma B when B is different from A. And let me put a C here so that we don't get confused. This is just a dummy index. So when I do that, I get a matrix here that generically has as elements SAB over sigma A, sigma B squared. Okay, that's the generic element here. What's the one that is a little tricky to compute? The diagonal, exactly. So I'm introducing, this is a Jacobian with elements JAB, and the diagonal is the one you were supposed to compute because it's the one that is a little harder. But the diagonal happens to be JAA. You pay a minus sign, right? Because now it's in a different location, the derivative that you're taking. So you pay a minus sign for that. And then you get a sum over the rest because this A appears everywhere. So what did you discover? That this matrix J is equal to whom? Is equal to the matrix phi that we discovered over here. So J is nothing but the matrix J is the matrix phi. And now we're not surprised that we couldn't do this integral because this matrix phi has 3 null eigenvectors. And it's telling us to define something that makes sense. We're supposed to compute the determinant of the Jacobian and put it into the integral. That's the way we compute integrals that have delta functions, right? So the fact we couldn't do it is because the Jacobian has 0 determinant. But now we have a fancy way of defining the determinant, right? We can remove 3 rows and 3 columns. Now, removing 3, if this index is our row index, A, removing 3 rows means what? Removing 3 what? 3 equations, which is great. For 4 particles, we know we had to remove 3 equations. So we remove 3 equations, any 3. And removing 3 columns would mean what? Removing what? Just look from here. So the rows are controlled by the equation you choose, and the columns are controlled by the variable that you choose. So somehow this thing is telling you that 3 equations are redundant and that 3 rows are redundant. So the rows are the coordinates. So it's telling you that 3 of the coordinates are redundant. Is that surprising? No, there was SL to C. We were supposed to gauge fix 3 puncture locations to any values that you like, and then get something that is meaningful. So this formula would make sense if we have to fix 3 equations, okay, 3 coordinates. Let me call them sigma I, sigma j, and sigma k, just by chance, okay? And second, I'm going to remove 3 equations. Which ones are we going to remove? Let me see. Oh, I cannot see. It's maybe EP, EQ, and ER. Those are the 3 equations I'm going to remove. And that means that if I compute the determinant prime of phi, which is also happens to be the determinant prime of my Jacobian, is going to be the determinant of phi that I had on the board. Let me see if I can show it to you. Actually, and this one down, and this one up. So it's going to be exactly that Jacobian over there. So if you have taken courses in string theory, you know that when you fix the SL to C redundancy, you pay the price of a Phi-F Popov Jacobian, and the price is precisely the determinant that I wrote there, the determinant of the differences of the puncture locations, right? So this equation can be written more precisely if I put a prime here as well. And the answer is nothing but, so let's write what this thing is. So we are supposed to sum over all the solutions of the equations, however many there are, okay? We don't care. Well, we should care, but not right now. So maybe I'll tell you how many, no, maybe you will get discouraged. So I won't tell you now how many solutions are there. So we do that, and what else do we have to do? Well, of course, we have to evaluate the integrand on the solutions. So the sigmas are the ones that depend on the solutions. So let me call I the solution space. So the sigmas depend on the solution. And what else do we have to put in here? Remember, we're doing this integral on the support of these equations. We are fixing the SL to C. And all that appears here is 1 over determinant prime of phi, evaluated at the particular solution that we want. Now, this is a precise formula that can be used. Okay, so why don't we use it? Well, the reason we cannot just go ahead and use it is that I haven't told you how to compute or how to determine these integrands, right? And I'm afraid I won't tell you how, because I don't know quite how to do it. But I can tell you the constraints this object has to satisfy, and we can start guessing integrands like crazy. And then, since we know how to evaluate the answer for anything, we can evaluate it and check if the answer agrees with any formula we have seen in the literature before, or that we know already. So constraints. On this integrand. Well, one very important one is that it should be nice and elegant. If you're just going to write something that is messy, and I'm sure it's possible to write tons of things like that, but hopefully we're going to be able to write something that looks nice in terms of the objects we have. But the most important constraint, actually, is the following. We have to construct something that allows us to build something that is SL to C invariant. From this point of view, this is very, very important. Because if we don't write something that is SL to C invariant, this could be as nice as you want, but this will change every time you change your choices. You make different choices for the punctures that you fix, and this thing will change all the time in a way that is not compensated by this guy. So you will be in trouble. So in order to fix this, we have to check how the measure transforms under a transformation where you send sigma to A sigma plus B, C sigma plus D, with A, B, C, and D, an element of SL to C. Okay? Very good. So we have that. If you have this product of differentials, you can check that this transforms as follows. It stays the same up to a factor that is of the form C sigma A plus D, product from 1 to n, square. Now, how about the product of the scattering equations? I'm assuming here, I'm pretending again that they are all independent, so this is meaningful. But you can check that the transformation that I'm giving you here is the transformation of determinant prime of phi. Okay? I'm just doing this for the counting. So this thing transforms, again, as itself, up to a factor that happens to be the same. So whatever our integrand is, it has to go and cancel these transformations. So I think I messed it up. This is minus 2. Okay? So we can now sit down and start computing, start guessing objects that would do this. Right? Well, the most natural thing to try is to try with objects that you already know. So one possibility would be to try with determinant prime of phi. Maybe we can stick that as an integrand. But then what would be the answer? So I'm giving you time. That was a question. So what would be the answer if we stick as the integrand determinant prime of phi? So that would be our first theory. So let's start theory 1. Our integrand happens to be determinant prime of the matrix phi that depends on sigmas and decays. And what's our amplitude? Very interesting amplitude we're going to get. What's the answer? The number of solutions, yes. It's 1 for every solution, so it counts the number of solutions. So now is a good time to tell you what the number of solutions is. So you agree, right? So you put it in here, so you get 1 for every solution. So this new theory computes for you the number of solutions. I don't know what that theory is, but it gives you n minus 3 factorial. OK, hopefully we're going to build something more interesting than this. Theory 2. Is it what?
Is it a valid QFT?
Something that has constant amplitudes. That's a good question. So, well, in 2 dimensions, right? In 2 dimensions, what you do is that you try to build theories by imposing that there is no particle production and so on. So here you will be constructing a theory and tuning the coupling so that at every order, you only get the new contact term that appears at that order. So everything else is 0. In 2 dimensions, you do the same thing by tuning the contact term so that you cancel the particle production. Here, you will be to cancel every pole up to, well, of course, it will be hard. You need tons of derivatives. So I don't know if the theory exists. But in any case, I'm not sure that we will be extremely excited. Well, maybe. Who knows? OK, I won't say anything. So let's try a different theory. So in order to find another theory, we have to find interesting objects that do something. So what would you use? So we said that determinant prime of phi carries all 4 units of SL to C transformation that we need. Now, if you go along the board, you will go to the next step and say, Pfaffian prime of A maybe does something interesting. So Pfaffian prime of A turns out to carry one unit. So you have to put 4 of them. Well, why not? So what theory is this? Well, I already told you last time what the theory was. But let's actually do a calculation and see what happens. Okay? So let's actually carry out, OK, why don't you try to compute the 4-particle amplitude in this theory? I'll be back in 10 minutes. And then get somebody from you to go to the blackboard and do it. If we had 1 hour and a half, then we could do that. OK. So let's do it. So for 4 particles, in lecture, I don't remember, maybe during the second lecture, we decided to use SL to C to fix sigma 1 to be 0, sigma 2 to be our variable, which we could call Z, sigma 3, we chose it to be 1, and sigma 4, we chose it to be infinity. Okay? So for the time being, I'm going to pretend that we haven't fixed sigma 4 to infinity. It's going to be just any value. And I'm going to set it to infinity at the end. Okay? So what am I supposed to do? Well, I'm supposed to integrate over Z. That's my only variable left. I could use this formula directly, but it's easier just to do it on the integral form, just to see what happens. So once we fix these 3 variables, we're supposed to put the little determinant 1, 3, 4 here, which I'm going to write explicitly so that we can save time. So we're going to write that it is sigma 1 minus sigma 3 minus sigma 4 minus sigma 1. So we're doing this because we're fixing sigma 2. So the remaining variables give me my 3 by 3 determinant that I'm supposed to put. Now, if you remember, when we did the example for 4 particles, we ended up naturally on an equation, one of the 4 equations we got. It was what we call now equation 1. So that's the equation I'm going to leave as an equation for me here, equation 1. And that means that I'm removing 2, 3, and 4. So I'm supposed to put the little 3 by 3 determinant for 2, 3, and 4. Of course, it didn't fit. And then 4 minus sigma 2, delta of equation 1. Now I'm supposed to put my integrand. But for 4 particles, so I'm going to choose to remove from my matrix A4. Remember, I have to remove 2 rows and 2 columns. So let me choose any 2 rows and any 2 columns. So remember, from the top here, I'm supposed to remove I and j. I'm going to choose I and j to be 1 and 2. So when I compute Pfaffian prime of A, I'm removing 1 and 2, so I'm supposed to put sigma 1 minus sigma 2 times the Pfaffian of the submatrix of the matrix A4 when I remove 1 and 2 and 1 and 2. So I end up with a 2 by 2 matrix. So it's the Pfaffian of a very simple matrix, and I think not even I can mess up this one. Well, you'll be surprised. So let's compute the Pfaffian of this matrix, which happens to be up to a sign that I'm not going to care about. Okay? So that's the Pfaffian of that matrix, which I'm supposed to put in here. So I'm going to put it S34 to the 4th power Now I'm ready to set sigma 4 to infinity. You see why I had to wait, right? I needed every single factor in order to have something that would converge or wouldn't give me 0 if I take sigma 4 to infinity. Now let's count. We have 1 power of sigma 4 here, 2, 3, 4, and I have 4 powers of sigma 4. So they all cancel out when I take sigma 4 to infinity. Now let me use the other parts of the gauge fixing to say that this is integral over z. So this is trivial. 1 minus 3 is 1 or minus 1. So this is 1 or minus 1. This one gives me z minus 1. Now I have my scattering equation, which happens to be something that we know very well. 1, 2, sigma 1, 2 is minus z plus S1, 3, which happens to be 1, minus 1, times this factor. And that factor is 1 over, what do we get? Sigma 1 is 0, sigma 2 is z, so we get z to the 4th. Now I'm supposed to do this complicated thing and hope for the best. Oh, and I'm missing a thank you, yes. I hope that's what you were saying and not, oh, this is so boring. I'm almost dying. If that's what you were saying, don't worry, there is only 10 minutes left. So we have this factor here, we have this, we're supposed to do this complicated thing. So let me write this as what? Let me pull out the factor of z, and let me put out the S1, 3 to write this as S1, 2 over minus S1, 3 plus z or minus z. When I do this, I can pull out this from the delta function and get something that looks like z minus 1 over here, z to the 4th from here, S34 to the 4th. This delta function doesn't give me any Jacobian if I pull this out. When I pull that out, what I get is z over S1, 3. So this gives me a 3 here. And hopefully this is going to make sense. And this, it has to be evaluated at z equals to minus S12 over S13. All right? The moment of truth, I'm sure it's going to work because Amit has been checking every single detail. If it doesn't work, it's his fault. Okay. What does it give? Anyone? You didn't compute it. Okay, so let's see. Z minus 1. Okay, let's start by turning this into ST and U, right? Because it's annoying to carry the indices. So S34, our convention is that this is also what? S. S12 is also S. S13, wow, what's happening with this? This is U. And S plus T plus U is equal to 0. So we get that A4 is equal to, so when we put this in here, we get a factor of U over S. We get S to the 4th, sorry, T, right? Because we're putting this into here, so we get a factor of T because it's Z minus 1. Then we get the S to the 4th. The Z will give us an S. What do we get? S cubed. And then we get U to the 4th. So what's wrong, Amit? So what do we get? So this is canceling this, and it's canceling all this, and we're getting T times U to the 4th. That wasn't supposed to happen. It doesn't even have the correct units. So what happened here? So I pulled out a Z, I got it here. I pulled out an S13, which is here, so that's fine. Very good, yes. So I'm missing this, which is a factor of U, right? So this gives me TU cubed, which is still wrong. Sorry, yeah, so it should be dimension 3. So what's happening?
I think the Jacobian of the delta function should be Z squared over S13. It's the derivative, isn't it?
No, I'm just pulling something from a delta function, so it just comes.
Yeah, but it's not linear.
It's just in the last step. Yes, thank you. OK, so let's see. So this guy gives me T over U. Oh, I didn't put that, right? So it's T over U. So 1 minus Z, OK. When you're in this situation, this is the best thing to do, right? I'm sure you all have done that, right? So 1 minus Z is T over, so when I put it there, T over U, right? Now S to the 4th, it has Z cubed, which gives you S cubed, U cubed, and then this guy is U, and this gives what? I don't know. So we cancel this with this, it's S. We have only one factor of T, and this cancels this and this. Huh? At least it looks nice and elegant. So that's criterion. Now, is this the amplitude of anything? So Yuji is going to ask right now, right? Yeah, so you don't have to ask. I already. All right, very good. All right, excellent. So needless to say, the whole confusion was planned in the talk and all that. Just to give you, so Last time we said that there was a fancy Lagrangian of a theory that appears sometimes in weird theories. At least I didn't know them. And the interaction Lagrangian, so this was a theory for a single scalar field. And the interaction Lagrangian was something strange. So I'm only going to write, since you took notes, I'm only going to write the term that we're interested in. We said that the theory that comes from this, or the conjecture, was that only the couplings that were even would give some power, would give some contribution. So we don't have a cubic coupling, we only have a quartic coupling. So I'm going to write what the quartic coupling was. So it was phi times the determinant of a strange matrix. It was a matrix made out of derivatives of the field. So the components of this matrix, if you remember, they were nu I, nu j, phi. So let's start here. So we're going to get 1 with 1 contracted. So we get box of phi. And here we get nu 1, nu 2 phi, nu 1, nu 3 phi. Sorry, the matrix was of size m minus 1. So if you're doing the quartic coupling, this is just 3 by 3. So I stop here. And then I have here nu 2, nu 1 phi, box phi, nu 2, nu 3 phi, and last one, and there will be higher order terms. Now, if we want to compute the 4-particle amplitude, since there are no cubic couplings, the answer is just a contact term. That's actually looking nice, right? Because our formula doesn't have any poles, which is kind of ironic. I started this whole thing saying that our moduli space was going to take care of all the poles and blah, 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 and now we got a formula that doesn't have any poles. Well, if we go to higher points, we will see the poles, and our formula will take care of them. But let's first check. So the whole amplitude is going to be the contact term. Now, once we take the Feynman rules from here, the derivative, the box, is going to be replaced by k mu of one of the 4 particles. But they are on shell, right? So this is going to be 0 for any one of the 4 particles. So in order to compute this complicated determinant, I'm free to set the diagonal terms to 0. So I can start from anything. So I'm going to get phi times, let me start with this guy, nu 1, nu 2 phi, right? I remove this guy and this guy. Then I compute this by taking this times this. So you get nu 2, nu 3 phi times this guy, nu 3, nu 1 phi. And now at 2 permutations, let me pretend that this guy is particle 4. This one is going to correspond to particle 1, particle 2, and particle 3. And therefore, I can compute this contact term by replacing the momenta with the corresponding particles. So I get K1, K1, K2, K2, K3, K3. And now the contractions are telling me how to do the dot products. So nu 1 is contracted with this nu 1 over there. So 1 is supposed to be contracted with 3. Nu 2 is contracted with this one. So these 2 guys are supposed to be contracted. And these 2 guys will be contracted with each other. And what I get is K1.K3 times K1.K2 times K2.K3, which is also known as S times T, I hope, times U. This is K2. So this is U, this is S, and this is T. So we found that this wasn't a crazy thing to do. There is a theory out there that does this. So I'm going to give you a reference. So you can find this is a special class of what are known as Galilean theories. And the special ones, which are theories that have more symmetry than the standard ones, was discovered or was constructed by, I mean, we discovered the S matrix first, and then, but the Lagrangian theory was discovered or was written down by these people here in all right. Very good. But I'm sure I can have 5 more minutes, right? So who is the, yes, thank you. Okay. And the reason is that we don't want to leave it here, because this is basically where we ended up last lecture, right? Exactly at this point. So we want to do something more interesting. Let's try and write more interesting integrands than these two. In fact, we have to step up the game because we want to introduce particles with a spin. So we have to introduce polarization vectors. Okay, so in order to do it, I'll take inspiration from our matrix A that we have written over there, and think about it as follows. You see that our object here, we had 4 powers of this, which can also be written as determinant prime of A squared. So it means that this guy actually came from doing a calculation that was using 2 matrices A. So why not get the object in one shot? So I want to compute this as the determinant of a single matrix, of a big matrix. Let's call it. What would that matrix be? Well, I will have to put 2 copies of the matrix A. So in order to do it, let me do it like this. And then what I'm going to do is that I'm going to put at every entry the intersection of these vectors labeled by the column and the row and divide by sigma 1, sigma 2. So here I get k1.k1, I'm going to put 0. k1.k2, I'm going to put k1.k2 over sigma 1 minus sigma 2. Remember, k1.k2 is roughly S12. Up to factors of 2, no problem. We get the same thing. So you get k1.k3, sigma 1 minus sigma 3, all the way to k1.kn, sigma 1 minus sigma n. And here again, we get k2.k1, sigma 2 minus sigma 1, all the way to kn.k1, sigma n minus sigma 1. I'm going to put a 0 here. And repeat the same thing everywhere. Perhaps I can put a 0 here or a 0 here. But I think even if I don't put zeros here, if we compute the determinant of this thing, well, I'll have to put zeros here. And then if I compute the determinant of this object, I'm going to get the full answer for this guy. Now I want to introduce polarization vectors. So what should I do to introduce polarization vectors? Well, you see that I'm repeating the information of the momentum here and here. So one possibility would be to replace the information of the momenta here by the information of the polarization vectors. So we have a collection of polarization vectors. So let me do it. I'm going to replace the information of the polarization vectors. The reason I'm doing this way is that I'm assuring myself that at the end of the day, I'll get something that has the correct SL to C weight, because I started with something that did. So if I mess around with the object that has correct SL to C weight in a way that I don't change too much the position of the dependence on the position of the punctures, then I'll end up with something that has correct SL2C weight, which was the condition for constructing an integrand that made sense. So if I replace this by polarization vectors, and the same thing here, I get something, well, almost everything is fixed except for this component, but we know that Ka dot epsilon A is supposed to be what? It's 0. So we can put a 0 here. So we get, so according to this, we dot K1 with epsilon 2, sigma 1 minus sigma 2, all the way to K1 epsilon n, sigma 1 minus epsilon n. And here we get K2 dot epsilon 1, sigma 2 minus sigma 1, 0, all the way to Kn dot epsilon 1, sigma m minus sigma 1, all the way to 0. And then on this side, we get epsilon 1 with epsilon 1. So you say epsilon A dot epsilon A. It's also 0. So it makes sense to write this as 0. And we get epsilon 2, epsilon 1, sigma 2 minus sigma 1, all the way to epsilon n. Now you're probably bored. But I promise that something nice is about to happen, which is not the end of the lecture. OK, so you construct this matrix. It has the correct SL2C weight to be an integrand. It seems nice and elegant. Now, hopefully, it does something interesting. If we are supposed to describe gauge bosons that are massless, so these are gauge bosons, right? So these guys are supposed to be massless. So, and we are describing them in terms of polarization vectors. We know that polarization vectors contain more information than what we need, so we have to impose what? A redundancy. So we need gauge invariance. So we need, if you start with this, somebody starts with this polarization vector, and I replace it, and somebody else chooses this one, we are supposed to get the same answer, right? Well, imagine that you were computing the determinant of this object. And you made your choice of polarization vector, say for particle 1. And somebody chose something else for particle 1. What would happen? Well, everywhere you see the polarization vector 1, you're shifting that by this much. And what you find is that the other person has the same answer as you, but that person has the same column that you did, shifted by a column that is identical to the first column. But if you're computing the determinant, such a shift is completely irrelevant. So this matrix is manifestly gauge invariant. So let's give a name to this matrix. Let's call it psi. Let's call it psi y. The y is going to be clear tomorrow. So let's call it psi y. So this matrix will give, if we compute the determinant of this guy, will give our third theory, which sadly is not any theory that I know. Maybe you can try and find what theory this thing will compute. But let me tell you a couple of things about this theory. First of all, the polarization vectors, it has how many copies of polarization vectors it will have? I'm computing the determinant. If I rescale the polarization vector 1 by t, that's the trick that somebody used earlier in the lectures, then this whole thing scales with t, and this whole thing scales with t, so it has a t squared. So whatever this thing is bilinear in polarization vectors. So for particle 1, it would look like this. And so on, times a tensor that will contract all these things. So it definitely doesn't look like a gauge theory, at least not a theory of spin 1 particles. If anything, it looks like a theory for spin 2 particles. So it's a little strange. You would fix that problem, you would say, by realizing that this matrix is antisymmetric. So you could also compute yet another theory by computing the Pfaffian of this guy. Instead of using the determinant, you will get the Pfaffian. And if you compute the Pfaffian, you're still missing factors of SL2C weight, which you could compensate with something else that you know, this Pfaffian prime of AN squared. And this will have the correct SL2C weight, and it would be linear in the polarization vectors. But still, it's a theory that I don't know what it is. Okay? So I'm afraid I'll have to stop here, because we have to stop somewhere. So this time, instead of giving you a Lagrangian and a theory that you're supposed to find what the theory is, I'm stopping with kind of a failure. We fail to construct something that I know, or a theory that somebody knows. But whatever it is, if we could fix it, if we could fix these things, they look very close to a theory that has gauge bosons, just particles of spin 1. And this one would even be more exciting. If we could fix this thing, we would get a theory of spin 2 particles. And that's what we have to do tomorrow. Okay? So let me stop here.